Okay, everyone. So today we will talk about the second half of the predicate calculus. So today's class is gonna be a little bit tricky, a little bit hard. So you have to follow me. If you think you get lost, please let me know. So yeah, if you get lost at some point, at some circle, there may be some problem there. So please let me know if you feel lost. Okay. So before we start talking today's stuff, let's have a little bit review of what have we learned on Monday. Okay. So anyone remember what's the thing we learned on Monday? We learned something about predicate calculus, right? So basically, let's not look at all those descriptions. So what is the predicate calculus? So we learned predicate calculus based on the propositional calculus we learned several weeks ago, right? We all know what is propositional calculus. We have those variables connected by those operators, conjunction, disjunction, those things. So here in predicate calculus, we replace the proposition with something called predicate. Okay, with something called predicate. So what is a predicate? If you remember, on Monday we did several exercises. How can we convert a sentence from natural language to predicate calculus? Right? If you still remember what we did there, predicate is something like you can use those operators to compare variables, integers, and compare the variables and integers, the combination of variable and integers. Like if the temperature greater than 30, temperature greater than 30, like temperature greater or equal to 30. So this whole part, it has a true or false value. If the temperature is 40, then it can return a true. If the temperature is lower than 30, if it's 20, it returns false, right? So this thing can return a true or false value. And this is one type of predicate. Another type of predicate is we use something like a function in the program to represent the relationship between two variables, right? For example, here we have this something like the function computer state, and has two variables, main and monitoring. How can we translate this? Is the main computer has a computer state which is monitoring. The subseed computer has a computer state, the value is monitoring. The same. So we use this kind of structure to represent the relationship between the main computer and the monitoring. The relationship between the subseed computer and the monitoring. Monitoring is a state of the computer. The idle is the state of the computer, and maybe idle is the state of another state of the computer, or shut down or not connected is another state of the computer. But here we translate this from the natural language, which states only when the main computer is in a monitoring state, while the subsidiary computer be in a monitoring state. So in this sentence, it doesn't only provide you with the relationship of the equality between those two computers. It also provides you with the information that both of the computer has the state, computer state. Both of the computer has the computer state, and the computer state in this case is monitoring for both of them. Okay. if we change that to only when the main computer is in a idle state, where the subsidiary computer be in a monitoring state. This is going to change to computer state main idle, computer state subsidiary monitoring, right? Okay, so that's predicate, what we got from the predicate. Okay, like we can do something like this: main react temperature greater than 1,000. And we use this temperature main reactor. Main reactor has a temperature, which is the main reactor temperature, and the main reactor temperature greater than 1,000 implies the monitoring in alarm state. And this also means monitoring has a state which is alarm. Okay. Yeah. And we can connect them with conjunction. Well, it's more like the propositions. We replace proposition. We replace the proposition with predicates. So, and we can connect. We can also connect them with a conjunction, right? Those implication, disjunction, those things. Okay, so that's not hard. Just yes, question.
Why isn't the term calculus used? Because there's no derivative or integral in any of these equations.
Are you talking about the actual calculus, the mathematic concept of calculus? Yeah, it's different from that part. Here we are trying to represent everything mathematically, and this calculus here means we are actually using some formal method, formal specification to specify those things mathematically. And the calculus here, how to say that?
But I don't see transforming a state with an integral or a derivative.
Yeah, just don't.
And that's what I would. When you say calculus, that's immediately what I think is that you're making a derivative or an integral.
Yeah, if you want to go to that part, you need to have an exact meaning of calculus. It's not only saying the not interested. Like finding properties and derivatives and intervals of functions by method. So this is the thing you are talking about. And here, the second thing here, particular method or system of calculation or reasoning. Okay, so calculus does not only mean this part. We have another meaning for calculus.
Okay.
So yeah. So most of that we're doing here is about reasoning, the logic. Yeah.
Okay.
It's not that calculus you're talking. Yeah. All right. Right now, let's go to today's stuff. Today we will introduce two modifiers, which is pretty fun. Set. Okay, we kind of talked about the set already. How can we specify the set? In the very first class. I'm afraid you already forgot, so let's have a little bit of review. So how do we specify the members of a set? First thing we can do is the enumeration. We list everything there, but it's not efficient, especially when you have a set, maybe a bigger set has 1,000, maybe infinite number of elements. Okay. So here we use this comprehensive specification to specify this set. Okay, so three part: signature, predicate, and term. They're separated by the separator and this dot. Okay, so what is signature? What is predicate? What is a term? Let's see an example here. Let's skip this definition, but we can directly see the example. Okay, all right. Signature, predicate, term. Let's say term. Term is the easiest thing to understand. Term is the actual thing that is inside this set. Okay, here the term is x squared, and then but the value of x squared is in this set. Okay, that part is easy. Okay, but what is the signature? What is the predicate here? So one thing is the signature, which gives tells you what set this element belongs to. Here the n is natural number, and obviously here we count 0 as natural number. Okay, so here n is the natural number, and if we do not look at this part, if we do not have this part, x less or equal to 5, we will have x n and dot x squared, which means x belongs to natural number, and every natural number square is in this set. Okay. However, we put another predicate here. We put this separator here. This thing is used to further give the modifiers or give the restrictions on this part, on this signature. Okay, so that here we know x belongs to this natural number, but here we give a modifier. We modify that. We'll have a further restriction: x should be less or equals to 5, so that x becomes 0, 1, 2, 3, 5, and then x squared is put into this set. So it's three part. And we can omit the middle part. If you think you do not have any restriction there, we can just say xn dot x square x square. So also this is a translation. The set formed from the natural numbers x such that x less or equals to 5, consisting of the squares of x's. So denotes some declarations. So this same thing, three part declarations. Okay, P is the predicate constrain the values. Okay, here, and E is the expression denoting a term. Okay, three part. Dot, after the dot is a term. After the separator is the P to constrain this signature. The vertical bar is the constraint bar. Separates the declaration from the constraint. Heavy dot separates the constraint from the term. Yeah, this is how we omit the constraint and the constraint bar. X natural number, x the square is the set of square natural numbers. Okay, so this is a little bit review of the set. So then we have this knowledge. Remember that how we specify the set. Then let's do something with set comprehension. Let's have some fun with this part. Set comprehension is a way to define set. This is an example. We see that already. Okay. Quantifiers. Two quantifiers. Okay. This is the key part of today. Two quantifiers. So propositional calculus is unable to adequately express statement about the properties of classes of objects and to reason about them. That's why we have all this whole predicate calculus thing, because propositional cannot represent this logic greater than those things. So that we have this what we learned on Monday, and today we will further extend the capability of the predicate calculus with two quantifiers. So what we need is a mathematical shorthand for expressing the propositions that hold for a class of the object. So we will use two operators known as those two. Remember how they look like? Existential quantifier and the universal quantifier. Okay, what do they mean? First, let's see what is existential quantifier. So if x and y are integers, then the truth value of x equal to y squared depends on the values of x and y. So x and y are the free variables of the predicate. Okay, so if we have this thing here, x equal to y squared, is it true or false? We don't know. It depends on what values is x, what value is y, right? If x, y both equal to 1, then this is true. If x is 1, y is 2, it's not true. Okay, so they're called free variables. However, here, how can we use the existential quantifier to specify this relationship? Okay, so this says there exists, or for some. If you put this quantifier in front of the x equal to y squared here, okay. Again, we see this part is a set. Okay. So y signature of y. What is z? Anyone know what is z? Integer. Have you learned that somewhere? N is a natural number. Z is integer. Okay. Z means integer. All right. So for the integer, for y is the integer, and this dot means the x equal to y squared. As I mentioned, if we do not have this quantifier here, whether this is correct, it all depends on what value is x, what value is y. However, if we put this here, existential quantifier means there exists. Here it means there exists a y, just there exists a y, or one or more, but it exists. Such y exists for some y. It can be one or more. For some y, which is the integer, we have a x, we have a value that is y squared. Can we find, so is this correct? Do you think is this correct? Will this return true or false?
Depends on what x and y are.
If we remove this, yeah, it depends on x, y. But if we put here, the whole thing becomes there exists an integer y such that x equal to y squared.
So isn't an integer and a natural number the same?
Oh, no. Integer includes negative numbers. Negative -1, -2.
But, okay.
But natural
Natural's
number,
only constant.
natural number, yeah, I hate this part. Natural number, you can, it's something like you're counting something, like 1, 2, 3, 4, 5, 6. But another theory is 0, 1, 2, 3, 5, 6. Okay. So natural number is either start from 0 or 1. Two theories there. Okay, but integer is it's not starting from anywhere. It has all those negative numbers. So there exists an integer y such that x equal to y squared.
So it can be true if it's 1.
Let's see. Yeah. There exists an integer y such that x equal to y squared. Yeah, this is true. Can you, if you don't think this is true, you can give me a value of x of y that make this not true. So to meet this, there exists the integer y such that x equal to y squared, right? So for that's the same as for every integer. Actually, for any integer, we can always find x, which is its square, right? For 2, if y is 2, x is 4. We can find its square. Okay, then that is true. We can find a integer that x equals to y squared. As long as we can find 1, this is true.
Right. Okay.
Yeah.
But I mean, that's the language there exists. An integer means that you only have to find one instance where it's true.
Yeah. Exists. You don't have to find 1. As long as there's 1, it will be true. So existential is always followed by this quantifier is always followed by a declaration. So it is followed by a heavy dot and a predicate being quantified. So here we only have this dot. We do not have any quantifier here. But here we can if we do not look at here, this is similar as a set, how we define a set, okay? Okay, this is another example. Here the existential quantification, the declaration is modified by a constraint. Everything's here. N, there exists an n, which is a natural number. And n is a natural number, and n is less or equals to 10. And n squared equal to 64. Do you think this is true or false?
It would be true. The number is 8.
Yeah, number is 8. That's a fast. Yeah, so the number is 8 because we can find an n. We can find an n. That means there exists an n. Okay, there exists an n. And less or equal to 10. Make its square 64. Okay, Now here, if we switch this n to z, is this correct?
Yes.
Yeah, 8 is one of them, and actually -8 is another one, right? Okay, if it's n, if we change this to z, okay, and this less or equal to 5, not 10, less or equal to 5, is this correct?
No.
Why?
Because you can't get to 8.
-8.
You just said it was n.
Yeah, I saw change to z. Sorry, I said change to z. Yeah.
I'm sure.
Yeah. So to z less or equal to 5, then after the dot, we can find an n that meet this condition. Yes. Okay. Very good. So there exists. It's pretty easy to meet this condition, right? As long as it's 1, we can make it happen. There exists a natural number less than or equal to 10, whose square is 64. Okay, another thing is universal quantifier. Says everything of a certain kind has a given property. Okay. Everything. One is there exists. The other one is more strict. Everything. It's a universal quantifier. That's why it's called universal. For here, all right. For every y, which is an integer, for every y, which is an integer, and y squared greater than x, we can find y squared greater than x. Does that make sense to you? Yeah. So here, there's a translation here. For all y that is integer, y squared greater than x, or every integer has a square that is greater than x. That is greater than x. Can we see, is this true or false? Let's think about it. Okay, for every y, we need every y to meet y squared greater than x.
What's x?
Yeah, what's x? That's a problem here. What's x? Right. If we see y, if we see y is 10, is this correct?
No.
No, because we can easily find something that is like
Okay.
if y is 1, y squared is 1. Y is not greater
If x
than.
is negative, it works, but
Yeah. Yeah. So this is not this. If we have this standalone here, it won't return a true, or it depends on the what x is. If x is just anything, any number, it depends on different definition of x. But yeah, I cannot find any value actually. If x is 0, y is 0. No, 0 is also integer. So this whole thing is wrong. This whole thing is wrong. Yeah, because you cannot find any x which meet this condition here, right? Don't you think so? So
I mean, you can make y4 and then x1.
it's very strict. So every y, every integer, y, actually we can use any value as long as it's integer. Put them as a y, and y squared greater than x. if x is any integer or any number, we can always find a y that is less or equal, y squared less or equal to x, because if x is 0, y is 0, they're equal, and if y is 1, is that greater than 0. Anything square is greater or equal to 0. Remember that? Yeah. But if x is negative number, this is going to be true, right? So it all depends on this x. Yeah. So like the those two quantifier, they are basically the same. You can use the three things: declaration or signature, then a predicate, and give a all the constraints on that signature, then dot the term there. Declaration, have a dot, quantify. Okay. So there might be a constraint on the declaration, and so the constraint bar may be used, and you can omit that bar as well. Here's another example. For r the n, which is a natural number, and n less or equal to 10. The n squared less or equal to 100. True or false? Is it true? Yeah. Yeah, it is true. Yeah.
So, what's the difference between the upside down A and the E? They seem to be the same.
What's that? Upside down A, yeah, that's R. And E is the exists. That's the reverse E. You mean the difference between the reverse E and upside down A?
Right.
Okay. The E, the reversed E is there exists. And upside down A is all of them have to meet this condition.
Okay.
Yeah. One is existential, one is universal. Right? Like one of us is a teacher, or all of us is all of us are teacher. That's this kind of difference. Okay.
Mutually exclusive within the set.
Yeah. Constraints bar. Okay, here this part is going to be kind of hard. So it's mixing it is mixing the those two quantifiers. All right. So if a predicate begins with two quantifiers, one existential and one universal, don't switch their order, of course. We're not switching their order, but here is an example of this. Can anyone translate this to sort of natural language? First, Rx integer.
Would you have to work the bracket, the inside bracket first?
And you don't have to evaluate. I'm not saying you have to evaluate this to be true or false. Okay. Here, this bracket means this is a section. After the dot, this is, remember the three part declaration. The declaration as a predicate and the terms, right? So this is the part that after the dot. Okay, just see them as the integrated part. All right, and then outside we have this x integer and dot blah 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 blah. What does that mean?
So,
For all x belonging to integers, there exists an integer y such that y is less than equal to x.
Can you say it again?
For all x belonging to integers,
Yeah.
there exists an integer y such that y greater than equal to x.
Yes, exactly. That's exactly what this expression states. Okay, so for all the x that belongs to integer, there exists a y, which is integer, and y is greater than x, which also means for every integer we can find another integer. We can find one integer that is greater than that integer. Okay, that is what it states here. For every integer x, for all the integer, all the integer x, which belongs to the integer. Okay, there exists a y that is also integer and y greater than x. Means for every integer we have for every integer x we have another integer y that is greater than x, which also means for every integer we can always find another integer that is greater than it. Is this true?
As far as I know, yes.
Yeah, this is true. Because if you can find any value, you can assume that p is an integer that we cannot find any integer that is greater than p, as long as you have a p plus 1. By definition, p plus 1 is another integer. It's greater than p. So this is true. Every integer we can find another integer. Given an integer, we can always find one bigger than it, which is true. Okay. But here we have another one. And how about this? I put but here. Probably you know the result. But can you translate this into natural language? Think about it.
There exists some integer that every integer is less than it, which that doesn't make any sense.
Yeah.
Because it would have to reference the sum at the
Right.
included.
Right. There exists an integer which makes every integer is less than that integer. There exists an integer y which makes all the integer x less than y, less than it. Right, that's kind of a biggest integer. But there doesn't exist biggest integer. There's no such a thing there.
I mean, even if there was, y can't be greater than itself. So
Yeah. Yes. Can find an integer that is bigger than all integers, which is false. Right, that is false. Yes. Yeah, here we further mix this expression with all those an expression which is quantified is itself a predicate. Yeah, it's a predicate and can be used as a predicate which can be connected by all those operators we talked. Conjunction, used in conjunction with other predicates. Let's see. So predicates can be formed from quantifiers and the standard propositional operators such as and, or, negation. Okay, here's some exercise here. Come on. Okay, 3 of them. Try to translate them into. Let's do the first. Let's do the first. So, T, transactions. Transaction state. T, valid. How can we translate that? There exists a T which is transition. There exists a transition T for which the transition state is valid. Okay, there exists a transition T for which the transition state is valid. Okay, remember that structure here? That represents the relationship between T and valid. So T has the transition state which is valid. Okay, that is a function there. Represent this relationship. Alright, so here, okay, so that's the first one. Now take out your pen, grab a pen and a piece of paper. Try to translate those two things into natural language. Okay. So put your pen down when you finish so that I know how many of you have finished. Finish. Okay. Let's have. I need one volunteer to tell us about the second question. Anyone? Yeah.
There exists a reactor that is connected to a functioning monitor.
There exists a concurrent reactor that is connected to a functioning monitor. Yeah, it means that. But if we want more
And wouldn't you say
specified, yeah,
connected?
yeah,
So I was going to be more formal with the
Yeah,
language.
more
There
formal.
exists a current reactor R and an allocated monitor M such that the M is functioning and connected to R.
yeah, something like that. There exists two things. First, there exists a current reactor R and a allocated monitor M. They all such that the allocated monitor state is functioning and it's connected to R. It's connected to that reactor. Yes. Okay. How about this third one? The VDU thing. I need another volunteer.
There exists allocated VDU such that if VDU state is on, then global status is active.
If we wanted to be more formal, you said the global status is active. If we want to be more specific, the VDU's global status, is active. So let me repeat it a little bit. So there exists an allocated VDU such that if that VDU state is on, then that VDU's global status is active. Okay. So this pattern there, as long as you follow that pattern, it's not that hard to understand, right? As long as we can somehow, so if when we are translating those implications, it's the same as if-then when we are doing the propositional calculus. So here, VDU state, it's the same thing. Just we've learned how to convert this part into natural language. We learned how to convert this structure into natural language. We learned how to convert this quantifiers into natural language. What we are doing when we combine them, what we want to do is mapping them to the logic into our natural language. So you need more practice on that. So
when you have the dark dot, what language would you replace that with?
Here, yes, such that is a good thing here, or which makes blah blah blah. They are same thing. Similar. They're similar. Maybe you can have some other words to connect them, but I often use such that and which makes things like this. Yeah. All right, let's do it another way. Convert into predicate calculus. Let's do this together. One of the Q will always be in an active state. One of the Q will always be in an active state. Think about it. One of it, so it must be something like E. That exists. One of. Yeah. In active state. Alright, let's look at the answer. Okay. This is Q, available Q state. Waiting status. Okay, this part. I think this is wrong. I think this is wrong. Yeah,
Where did that wait status come
there's
from?
no wait status. Let me modify it a little bit. Sorry. Page 7. In case I forgot.
So what
Yeah, question?
you're making the assumption that you're one of many, so you would automatically say the available queue of queues.
One moment. Let me put this there first. Okay. Question? Sorry, again.
So when the answer says available queues and the queue state is a function, you would automatically make it a function.
This is not a function. This looks like a function, but we would not call it function. It is a structure that represents the relationship between the queue and the active. As long as we want to represent any relationship between two things, in predicate calculus, we use this structure.
It's similar to a function.
Yeah, it is similar to a function, yes.
I mean,
But it has the more restricted rule to translate it. The queue has a queue state, which is active. But the function, you can define function anything. So like a Boolean function, But Boolean function can also be like a compare, maybe compare 1 and 2. It will return a greater or equal, something like that. But here, it's a queue state, basically, which means the first, we have two variables there, the first and the second. So this is something that belongs to the first. It can be a state, a status, a temperature. Maybe it's a person. It may be a height. It may be it's an age, gender, affiliation.
you could call that an attribute.
Yeah, like an attribute. Yeah, like an attribute. Something
And
that
then
something
the
that
second
describes
portion
this.
is, you know, the verb or the action associated with the attribute.
Yeah, the attribute. Yes. So queues at one of the queue, we're representing the queue's state. Active. Yeah. So here, if we do not look there exists available queues. Available queue. There exists available queue, which the queue is active. So it's same as one of the queue will always be in an active state. Yeah.
So since it's interpretation, a lot of it is how you transpose the language into formulating a sentence.
Yeah. If
There's
we
a lot of subjectivity to that.
If we convert from natural language to formal specification, there is a chance that there's ambiguity in the natural language. We have a different kind of formal specification. But if we translate from formal specification back to the natural language, it should be fixed. Because the formal language is strictly defined. As long as you convert it correctly, without those ambiguity, use strict language. It should not. I'm not saying the language is fixed. I'm saying the meaning is fixed. The meaning
Right.
behind is fixed. Yeah.
But in my industry,
Yeah.
you try not to take the language and transpose it into something that your customer can't understand. And formal specifications is taking a set of instructions and formalizing it into
Yeah. Formal
something
specific.
that's a little bit higher. You can show this to your customer and expect them to follow along.
Yeah. So formal specification, it has the pros and cons. One that thing you mentioned is one of the great disadvantage there, because not everyone can understand this formal specification. However, formal specification can be applied to not only the customers. If you're thinking about human communication, formal specification can definitely help you to avoid this ambiguity. But the condition is both parties or all the parties have to understand how to read this formal specification. However, if you think about the communication between human and computer, if you want to do some automated programming work, like your computer doing some automated programming work, you kind of want to specify this requirements first. Okay, at this moment, will you choose the natural language or this formal specification to communicate with the computer? This is way much easier than natural language, right? Yeah, but that thing, it is the reality. Yes, customers, if they are not trained, they do not like to look at this at all. So something that restricted the application of a formal specification, but it does has a value there. Yeah.
In industry, you just basically use formal specifications when you're talking to a machine or referring to a machine language.
Oh, okay. So I think during the
it's like UML. If everybody understands the language, it's great. If everybody doesn't understand the language, well, then you have a problem.
Yeah, like what I mentioned, in this first class, actually first several weeks, I mentioned there's a lecture we talk about how people are using formal specifications. So it depends. It differs from place to place. Actually, formal specification, if you think about those industry in other parts of the world, like in Europe, it's more popular than that in the U.S. But if it's in one place, it is also different from different application areas. If it's a security sensitive industry, you want to use they turn to use this formal specification because they want everything to be strict, but strictly defined. However, if it's some company that they are pursuing too fast to produce their product fast, especially for those internet companies, they want everything fast, so they can go ahead of other companies. They can push their product online faster. Probably this is not a good idea for the communication. Yeah. But it does has a value there. Okay, let's continue with this one. This is a little bit harder, longer. One of the actuators will be functioning provided that the system ambient temperature is within safety limits and the main reactor is not in a warm-up state. The current safety limits are 10 to 100 degrees centigrade. Here we can say it's saying centigrade. It's not the unit in the US. It's an example from the book, so it must be come from some other places in the world. Reactors will be functioning provided that system ambient temperature. Okay, let's. I would not have enough time now, so let's look at this. Look at this solution here. Yeah. So this E is after this implication. Yeah, because all of our examples we put that like E or the A in front of at the first place, but here it's just telling you this E can exist somewhere else. It doesn't have to be always in the first put in the first first thing of the expression. Okay. It doesn't have to be
swap
first.
those,
You can swap this and this and, so all those things you can swap. Yes, but
you can swap the E and put it in front if you wanted to.
in front.
Yeah, and take the you just swap
Oh, yeah.
the whole statement.
Let's see. If you put this E here, if there exists an A. If there exists an A which is act such that if this is then blah 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 blah. Yeah. If you put this E here, you have to then put this whole part. E A X there. And the dot here. Okay. Let's see. Yeah, let me double check, make sure if I can put this E in front of it logically. Limits. Yeah. Yes, we can put the E in front of it. But this whole set includes this dot if you want to put it in front of. Okay, so here do we need to explain it? So first let's see reactor status. The main reactor status is warming up. It's not warming up. So open negation here. It's not warming up, and the temperature less equal 100 greater equal to 10. Then there exists act that its state is functioning. It's the same as here. That's what we mentioned here. Any problem here? So can everyone reach something that is familiar, like similar to this one? Either the E is here or in front of it. Okay, everyone
I put the
clear with this? Yeah. Well, what is your answer? Can you write it down? Or, yeah. It should be reversed.
I was trying to break down.
A one actor. Oh, I got you. So that is not actually correct. Cause A's you got the conditions and the result reversed.
Mm-hmm.
Yeah, basically.
But okay. So
Yeah, the implication is reversed. Yeah.
I got you. Safety limit. Is this notation if you made it like 10 greater or equal to 100 Celsius degrees? the function is a safety limits is afterwards, so it's a range value is in the
So
function.
most of the time, when you have this kind of structure here, this is usually objective. But here, yeah, I know the meaning is there. But first, this thing is reversed. Right? We agree that this thing is reversed. And this is not something that you're really seeing.
It's my short hit.
So this is yeah.
Because
This
I
is easy.
typically would not write out the.
That's meaning is there. I know you put this as limits, and that is kind of like an adjective to for the limit, right? Yeah. Logically, yeah, that small part is correct, but logically that implication is wrong. Yeah.
Needs to be in.
Okay, yeah. So we kind of need to practice to align our thoughts with this kind of description. That's why we need to practice. So this practice actually, if you trust your human brain, it's kind of create this connect those neurons to form to let us solve the problem. So next time after you practice, that's why we do a lot of practice for something. Next time when you are doing solve the same similar problem, all the neurons they are connected, so you can faster solve them with some pattern, right? Okay, translate. The last two things for today. First, translate the first one, the first expression, or the in belongs to. Yeah, can we do this as quickly as we can? Yeah. First one.
For all numbers n between 1 and 10, their n cubed is less than or equal to 1,000.
Yes, correct. So that's correct.
Yes.
Yes. And then the second one. Pay attention to this E, the V.
There is an exhaust valve that is either open or closed exclusively.
Not there exists, or.
Sorry, I'm sorry. All of the exhaust valves are either open or closed and cannot be both.
Yeah. Yeah, for all the exhaust valves, the valve status can either be open or closed. Yes, that's what it means. Yes. All right. I think that's okay. We have last thing here. Let's finish this, then we can finish the day. Here, all the P, blah blah blah, and the dot, an implication, and or another dot. Okay, let's try someone else. Yeah. Can somebody else volunteer to answer the last one? Come on, the last chance to shine yourself in the class today.
There exists a
Not there exists. We don't have any. They exist. It's or. We have two quantifiers. They are or.
for all progs in memory, such that the prog state is suspended, implies there exists all processors that are idle.
Okay. Do we remember the priority of the operators? Implies has the lowest priority. If we put, actually we should put the brackets there. The first line is a part. The second line after the implication is another part. So it's like A implies B. So we have the whole thing starts with the if. Okay, some other opinion? You have another opinion?
I was going to say the same thing.
Okay, Someone want to say, or I will say the answer. So if all the programs in memory's state is suspended, then all the processors state will be idle. Okay, if all the program in the memory state, if all the programs in the memory are suspended, then all the processors will be idle.
What gives it away to be if? What would you say if?
If?
What about the statement?
I don't hear you. What is that?
What about the statement makes you use if?
Oh, this implication makes us use if.
So
When we say this,
then-
this implication is what we evaluated last, but when we speak them out, it comes first. Okay, so that's kind of tricky. So so if the biggest picture is an if then, okay, and after the if it's all blah blah blah, then all blah 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 blah. Okay, all right, okay. I will post another homework here, then you can have some more practice of translating those things. Alright, there won't be a lot of homework, but just those that is enough for your practice and it won't take you a lot of time. Please do those exercises at home. Okay, alright, thank you very much for today.